so I think we can get started. So welcome everyone to the CS Colloquium at the Hebrew University. Today we are honored to have Roi Livni with us. Roi was a PhD student here at the Hebrew University, where he worked with Amir Globalzon. Then he was a postdoc at Princeton, and now he's a senior lecturer at the Tel Aviv University. And I had the honor to overlap with Roi during our PhDs, and the thing that I remember most about him was other than his great character and wise ideas, was his world record of winning 2 best papers in 1 week. And now today is going to tell us about the private case of fundamental theorem of learning. And without further ado, Roi.
Okay, thank you very much. So I understand it's in English to talk?
Yes.
Okay. So so I'm going to talk about the private case of the fundamental theorem of learning, which is kind of a joint project or a few works that we had in the last year. So before I present our work, so let's talk about what is the fundamental theorem of learning. So, what is learning first? So, what is a learner? I won't go into the definition because I assume that you saw it in many talks in the past. So but basically you have a learner that observed a iate labeled sample drawn from some unknown distribution, and it needs to output a predictor. And what it needs to do, we want that with probability 1 minus delta, the predictor, this is f, is epsilon close to perform as well as some class of predictions or functions that we want to learn. So that means you have some data, it is drawn from some distribution, you give it to the algorithm, you get a predictor f, and what needs to happen with high probability is that the error, the prediction error of this function needs to be close to the minimal error of the best hypothesis in the class. And what the fundamental theorem states is that we have the following characterization of learning, which says that a class H is learnable in the sense that we can, with enough sample, learn the class if it has a finite VC dimension. So the VC dimension is some, I won't go to the definition, it's some combinatorial dimension defined on the hypothesis class. It measures how many different patterns you might see on a small set, and as a characterization, it means that learning a class can be learned only if it has finite VC dimension. And the second part says that also the class has to have uniform convergence property. Okay, it's not. It doesn't mean that it also has to have you need both, but VC dimension also implies uniform convergence property. Now, what does the uniform convergence property say? It says that if you want to estimate the loss of every hypothesis in the class, then given some sample size, you can achieve that. So the empirical error will be close to the true error, not just for the optimal or for the hypothesis that you're learning, but in fact, if you have enough data, then you can measure the performance of every hypothesis in your class. So in other words, obviously, this will entail learning. If you can, by looking at enough data, you can estimate the performance of every hypothesis, then obviously you can choose the best one. But the theorem also said that it is equivalent, meaning the amount of data that you need to observe is so much that you can basically estimate the performance of all the hypotheses. Something that a priori you might think that you could do with much less. And finally, it also gives some, you could say, algorithmic characterization, which says how should you perform learning. That is, as long as you don't care about computational efficiency. It basically says, okay, so collect enough data, and then basically choose the empirical risk minimizer. So choose the hypothesis that works best on the sample that you observe. So this is a very classical result, and you could say it's the start of learning theory, which at least in the binary classification case, completely states information theoretically what is needed in order to learn. Now, then there is privacy, which is relatively a newer notion, which discusses mechanisms that get to observe data, and then they need to give you some output over the data. And what you want to make sure is that even though you release the information that you are required to release, the privacy of the data set is not compromised. And the definition states that a mechanism which gets to see a data set and provide some output is differentially private, alpha beta differentially private, if given a data set, if I replace it with a data set that is the same, but is different only in one row, so the Hamming distance between the two data sets is 1, then the probability for some output remains is non-negligible if and only if it is also non-negligible given the altered data set. So up to some constant factor, the probability remains the same, plus maybe some other term which is negligible in the size of the sample set. So this is a classical definition of privacy, of differential privacy, which is today considered the main definition we work with when we want to discuss private mechanisms. And given that
question, do you mean beta smaller than maybe 1 over the size of S?
Yeah, 1 over S.
So it's inverse.
Yeah.
There's also, sorry, there's a question from the audience. Somebody's asking, can you explain what is S prime? And
so you have a data set. S prime is a data set for every data set that is different from S by 1 column or 1 row, depending on how you put your data set. So you have a data set that is at Hamming distance 1, then you want that the output of the algorithm, given that it sees S or S prime, would have the same probability. Up to some factor will have the same probability. So nothing, you don't see anything out of the ordinary given S that you won't see given S prime. So if you take the data set and just change one element, let's say the data set contains patients, and one of the patients is me, and some hacker wants to discover if I am sick or not, then what he could do, he could look at the output and say, okay, given that he is sick, I expect this output, but given that he is not sick, I do not expect this output, and then he can basically find out if I'm sick or not. But privacy would make sure this doesn't happen. So if you see some output given one data set, by altering the data set by just one element will not change the probability of that output. Okay? And
this is only for the specific age that is output by the algorithm, right?
Yeah, so that the age is a function of the algorithm and S, right? It sees S and it outputs some age.
Can I ask a question?
Yeah, sure.
I just don't see how this bound is tight. I mean, because alpha is not bound, and so does, I mean, beta is bound to the size of the data.
So again, this is the definition of alpha beta privacy. So alpha beta are the parameters of privacy. So
we expect
the algorithm is, let's say, 1 over log n private if for alpha equals 1 and beta 1 over log s, this definition is satisfied.
Okay.
All right. And okay, so and then given so given this notion, it was very natural to ask the question, what can we learn privately? So what do we mean by to learn something privately? You have a class and you have an algorithm that satisfies the differential privacy constraint and is learning the class. Okay? So that's what you want to know when you study private learning. And this is a kind of a roadmap of some results that we had, which kind of give an analog picture to the problem of private learning with respect to regular learning. So let me just say that if we would want to have a complete analog, then we would need to also show this part. I'll talk about it in a minute. But and we're kind of close to it. So given this result, what these lines of work would show is that in some sense, private learning is similar to learning, where instead of VC dimension, we have a notion of Littlestone dimension, which I'll talk about and I'll explain what it is. But it's just an alternative combinatorial dimension. And you can show that private learning is equivalent to finite Littlestone dimension instead of VC dimension. And also contingents that we can show relation between proper learning and learning, which I'll also explain. You would also get an equivalence between private learning and another notion, which I will term here private uniform convergence. And for those who are familiar with differential privacy, private uniform convergence is just yet another name for notions that you are familiar with, like sanitization, private synthetic data, and so on. But in order to make this picture analog to the fundamental theorem, it is, I think, interesting to think of this as basically the replacement of uniform convergence with the requirement of private uniform convergence. Okay, so let me just introduce the people that were responsible to this result, my collaborators. So, so the result that private learning implies finite Littlestone dimension. This is joint work with Noga Alon, Mariante Mariales, and Shai Moran. Also, the result where we showed that private proper learning implies private uniform convergence is again with Shai Moran and Olivier Bousquet. And finally, the last result, which is now presented in Fox, is that finite Littlestone dimension implied private learning, which is a joint work with Mark Ban and again Shai Moran. Okay, so these are the three results that I want to talk about in this lecture, and I'll give just a roadmap. So now what I'm going to do is I'm going to go over these results. So first we'll discuss why private learning implies finite Littlestone dimension, and then the second result is why finite Littlestone dimension implies private learning, and finally I'll also talk about this notion of private uniform convergence and its implications. Okay, so.
By the way, there was a question at the chat. So people are curious, why is this, why do we think that changing one sample will influence the decision of the classifier? I mean, what's the intuition behind this concern?
Again? Why are we concerned that one
that changing just one out of many samples in the training set?
Yeah, okay. So yeah, maybe I should have written the definition a little. I kind of had the feeling that privacy is okay. So let's talk about what is privacy and why. So the thing is, again, so what do we want to do? We have a data set, let's say, of patients, and what we are worried about is that someone will find out information about the patient in the data set. Okay, that's roughly the problem. Now, what you don't want to assume is that this hacker, this person that tries to find out, is in some sense like passive and just gets the information. So you even want to assume that he hacked your data set, he contaminated your data set, and he made sure that once he gets the output, he will get the information that he is looking for. So unless you want to make some assumptions about this adversary that tries to breach privacy, you basically need to assume that he has all the information in your data set except for the information that he's looking for. So under this assumption, you want an algorithm that, given any type of input, changing just one column in that data set will not cause some change in the output too much. Okay, something that is improbable. So that's why you want to check what happens if you input the algorithm to data sets that are different only in one column. Does that answer the question?
I think so. Maybe just a small follow-up. I mean, maybe this is what you're going to talk about. But what are the chances that, for a random learner, changing one sample would influence the decision? Is it something that you need to enhance the learner not to?
Yeah, so that's what we're going to talk. We're going to see that for certain classes, you cannot achieve privacy. Okay, there are certain classes that are not learnable in this setting at all. And then we're going to characterize those that are learnable. So a random classifier will definitely not work.
Thanks.
Okay.
In follow-up to this question, can I ask again?
Yeah.
If I imagine a scenario with many samples, changing just one of them, like in a high probability, will not change the model much in any given metric. So kind of naively, we expect.
So first, I don't even know if it's true that by changing one parameter, you don't change the model too much. Depends on what is your model and what are you learning. And second, the question, what do you mean by too much? So even if you take like neural networks, naively, it is kind of known. I don't know if it's known, but naively, we kind of expect a neural network to memorize the data that it was trained on. So it shouldn't be that hard. Maybe if you go over the parameters and you look at the L2 distance, maybe you won't see a large distance. But overall, if you look at the performance of the neural network and you try to analyze it, it shouldn't be that hard to actually extract the data that it was trained on. Given that it is memorizing it, the information is there. So there's no reason to assume and sample from some distribution. Now, if you want to protect the privacy of your data set, you cannot really assume that, because there's always the chance that someone contaminated your sample. And so you cannot assume, for privacy matters, that your data is sampled iade. Okay? Or not convinced yet?
I think that I understood enough to stop disturbing.
Okay. Okay, so what if private learning implies finite Littlestone dimension? So before I even talk about what is finite Littlestone dimension, I want to talk about how we got to this question, because the original question that we were interested in was not so much about why does private learning imply finite Littlestone dimension. Actually, we were looking at a question that others were looking, which is a specific problem, whether the class of thresholds is learnable in the private sense or not. Now, what is the class of thresholds? You have a domain which is linearly ordered, and each hypothesis is defined by some point, and all points before it are -1s, and all points after it are +1. So this is your class, and this was for a lot of time was considered like a natural candidate for a class that might not be privately learnable. And indeed, in a work that preceded ours by Mark Bunn, Kobi Nissim, Uri Stemer, and Salil Vadhan, what they showed is that indeed thresholds are not properly privately learnable. So what does it mean by properly? Properly means that the algorithm needs to output a threshold function. Okay, you learn the threshold functions by actually outputting a threshold function from the class. And they showed that the sample size scales with n, where n here is the size of your domain. So if we're thinking of thresholds over an infinite set, then it is not learnable. Okay, if you care about finite sets, then everything is learnable. But what you want is you want to get results that don't scale with the size of the domain. And they showed that a lower bound for proper private learning of this class. What we did in our work is we extended this and showed that even in the improper learning setting, still the class is not learnable. Okay? And this had two major consequences. So you might think, why would I care about proper or improper? Other than that it is more general, but also improper has the following very nice property, that improper learning is inheritive. So what does it mean? It means that if a class contains a non-learnable class, then this class is also non-learnable. Because if I could learn the class that contains it, then I have improperly learned anything that it contains. Okay? So
there is a question from the audience asking to briefly say what's the difference between proper and improper.
Yeah, so like I said, so proper learning means that you need to output an hypothesis from your class. In the case of thresholds, it means that the predictor needs to be a threshold function. And improper, you're allowed to output any predictor you want. Okay? So what we show is, even if I allow you to output any predictor you want, the class of thresholds remain non-learnable. So the main, so one thing that you get out of this from improper, it means that any class that contains thresholds would also be non-learnable. Okay, so this is not true for proper learning. You might have a class that is not properly learnable, but it is contained in some other class which is now properly learnable. But for improper, you get this inherited property that if a class is not learnable improperly, then anything that might contain it becomes non-learnable. And as a corollary, what we get is that basically any class that has a finite Littlestone dimension will be non-learnable. And the reason for this is because of a result, actually from modular theory. It's kind of interesting how Littlestone dimension appears there. It is really has nothing to do with privacy or about learning, but it is a combinatorial result about this dimension, Littlestone, which I still haven't defined. And what Sherlock showed in 78 is basically that Littlestone dimension, any class with infinite Littlestone dimension would contain thresholds. So in other words, what we did in this paper, we showed the lower bound that shows that thresholds are not learnable. And because of this result by Shelach, it immediately suggested that perhaps what we need to look at when we look for upper bounds is on the Littlestone dimension. Okay, but it will be more relevant when we talk about the upper bound. But for now, basically the result private learning implies finite Littlestone dimension is not that different from just saying that the class of thresholds is not privately learnable. Okay, but it was an important message that we also discovered, that it means that the Littlestone dimension classes are not learnable, because it immediately told us what we need to look next. That what happens if the class has finite Littlestone dimension. Okay. So let me briefly go over the proof overview. One slide. The idea I had to show that this class is not privately learnable. So the main obstacle always when you talk about improper algorithms is that an improper algorithm is allowed to output whatever it wants, right? You give it some sample and then it can output any weird function that it might want. So we need to put some structure into the output of the algorithm. And the way we did it was using a Ramsey theorem. So first, what was the structure that we wanted? So we call it homogeneous algorithm, slightly because of homogeneous coloring in Ramsey. But what is an homogeneous algorithm? So think of an algorithm that given input, minuses and pluses, the probability that it will label a certain point as +1 or -1 depends only on its position with respect to the input sample. Okay, so all points before the first point have probability P1 to be labeled as 1. All points after the first point have probability P2, and so on. Okay, and I don't know the dependencies. The dependency can be wacky. Maybe they are iade, maybe they are all the same. I don't care about that. I just want that they will have the same probability. And the probability will depend only on the position of that point. Now you can basically show that, what you can show is that using Ramsey is that you can always find a subdomain where the algorithm will behave in this way. So what do I mean by that? So in Ramsey's theorem, what you need to do is you need to define some coloring over tuples in your set. And then what you do is you find an homogeneous set. You can always show that there is some set that has the same color. So what is the coloring that we use? We take basically n+1 tuples, and then we say, what happens if I don't see the first point? What is the probability that I label it as -1 or 1, doesn't matter. That's P1. And then what happens if I don't see the second point? How am I going to label? What's the probability that the algorithm will label it as +1, P2, and so on? So we have this vector. So for every tuple, we have a vector that defines the color. And then by Ramsey's theorem, we know that if the domain is large enough, we'll find a subdomain that the coloring is homogeneous. Now, it takes 2 minutes to think about it, and you see that basically an homogeneous coloring means that the algorithm behaves the way we want it on this set. Now, once the algorithm behaves in this manner, then to prove that it is not private, what you need to do is you basically need to find some sensitive point where by moving it, you change by a lot the probability that a certain point will be labeled as +1 and -1. And what do I mean by a lot? Well, it's enough even 1 over m, where m is the sample size. So that means that the probability to be labeled as +1 or -1 is very, very sensitive to the question whether this point in this example, the third point appeared at the beginning of the interval or at the end of the interval. So just by changing this one point, I can change the probabilities for certain points to be negative or positive. And using this sensitivity, I can breach privacy. Okay, so this was the high-level idea. Questions so far? Okay. So now, what I want to talk is the second result that shows that Littlestone dimension implies private learning. So like I said, in the result before, what we did is we showed that thresholds are not learnable. And the natural question was then, given that the set has finite Littlestone dimension, is it privately learnable? And in order to answer this question, now I do need to introduce what is the Littlestone dimension and how we used it in order to show that Littlestone dimension implies privacy. So to do that, let me go back to Littlestone's original paper where he introduced the notion. And then what he was interested about is a following model, which is now kind of known as a mistake-bound model. And it considers the following problem. You have a learner, and the learner observes sequentially X's, and then needs to choose predictions. And then once the adversary learner chooses, sees X and chooses the prediction, the adversary shows yi, the label, to the learner. And then the learner suffers a mistake if he predicted it wrong. Okay, so this sequence appears not stochastically. And the constraint on the adversary is that at the end of the game, there needs to be one hypothesis that is consistent with the labeling that he showed us. And we want to know what's the number of mistakes. And then Littlestone dimension gave a combinatorial characterization, which I'll give in a minute. And later on, it was also shown that this notion is also gives you the regret bound of this model, which can be thought as an agnostic learning. But this is actually not something that we needed for this result. So just let me give you an example for the mistake bound model. So let's say we want to learn the threshold class. So at each iteration, we have all the points, and at each iteration, the adversary chooses a point. Let's say it chooses this point. So we need to choose the labeling. What would you say, +1 or -1? You can gamble. Yeah, so let's say you want to say 1. Okay, so you're the learner and you predict this is 1. Now the adversary can do whatever it wants. The adversary wants to tell you, no, you're wrong, you made a mistake. So now you have one mistake, -1. But on the other hand, remember that the adversary needs to be consistent. So note that from now on, all of these points need to be labeled as -1. So even though we did a mistake, we now have some information, right? So we learned something. We learned that all these points are -1. If the adversary will ask us any of these points, we are not going to make a mistake. So the adversary now can choose any points he wants. Obviously, we will not choose one of these points because we know them. So he chooses to ask us what the prediction on this point. So how would you predict it? So note that if you predict it as -1, then if you will be wrong and it will say +1, then again, you will be able to predict correctly all of these points, and you will basically be able to narrow down the mistakes you can make. And you can easily see that in this model, over the threshold, you're not going to make more than log a mistake, right? Because you can always cut by half the number of points that you're going to make mistake on the next one. And given this game, you can also come up quite easily from what is the definition of the Littlestone dimension. So the Littlestone dimension is defined as basically that's the strategy of the adversary. So what can the adversary do? It can basically build some binary tree where at first it shows us some point x1. And then you can scheme what it's going to do if we say y equals 1. So it's going to show us some x2, and it's going to make us say we did a mistake over x1, and if we say -1, then again, it will say that we did a mistake, and so on. So we can build this tree. And obviously, the strategy, the number of mistakes it can inflict is the depth of this tree. So this is the Littlestone dimension, the depth of the largest tree that you can build in this setting, where you're constrained that every path in the tree needs to be realized by the hypothesis class. So now let me discuss how we showed that Littlestone dimension implies deep learning. So the proof idea is divided into 2 steps, where in the first step, what we did is we introduced this notion called global stability. And then, I'll talk about it in a minute, and then we divided the proof into 2 steps, where we show that globally stable learner implies private learners. And then we no longer need to talk about privacy, we just show that finite Littlestone dimension implies globally stable learners. So what is a globally stable learner? So a learning algorithm is globally stable if there exists some age so that the probability that the algorithm will output that age given some sample is constant. Okay, maybe small, but a constant. Now, here the probability is taken over both sample and random bits of the algorithm. Okay, so, and the age may depend on the distribution, but not necessarily on S. Okay, not on the data, but on the distribution. So this is the idea behind the notion of global stability. And proving that globally stable algorithms are private, it follows kind of standard tools from private learning, where the idea is to show that you can privately release histogram. So that means that if you measure the frequency of each element to appear, then you can output a noisy version of this histogram in a private manner. So once you can do that, it's kind of easy to privatize your algorithm. You just run it multiple times and obtain a sample of candidate hypothesis. And now you build the frequency or the histogram, and you output privately the frequency of each hypothesis. But because one hypothesis is very frequent, even if you noise this information, you still would see it in the output. So this way you can measure this way you will output some hypothesis. So that means that all we need to show is that online learnability implies global stability. Okay, and now we don't need to even think about privacy anymore. Okay, so we just need to ask, we have the following problem. We have an online learnable class. Can we somehow construct an algorithm that with some probability will output the same hypothesis every time we run it? So I'll give you a high-level proof of why you can do that. So first, let's start with a very simple case of Littlestone dimension 1. So remember, Littlestone dimension 1 means you have an algorithm that, given sequential data, it will make at most one mistake when it labels that data. So what we're going to do is, given iade data, we're going to run the online learner on the sample as if it was given sequentially, and then we're going to output the predictor of the algorithm. Now we're going to think of 2 cases. One, that whenever we do this on the distribution, it is unlikely that the algorithm makes mistakes. So basically, the algorithm goes over the sample and doesn't make any mistake. And the second option is that it's going to make one mistake. Now, this is inclusive because one of these cases has to happen because the algorithm doesn't make more than one mistake. Now, in the first case, when it doesn't make any mistake, then what you can basically show is that the hypothesis or the original state of the algorithm, the hypothesis in which it predicts before it even saw example, is already a good hypothesis because it generally doesn't make any mistakes. It's very hard to make it see mistakes. And because it's independent of the sample, it will be globally stable to just output it. And the second case is what happens if you have one mistake. So what happens if you run the algorithm and it has one mistake? So what I want to show in this case is that it's going to output the only single hypothesis that is consistent with the sample. And to see this, so suppose that eventually the algorithm outputs some hypothesis that is not the hypothesis that is consistent with the sample, the unique one, then it means that you have some x where they disagree, and then you can just make the algorithm makes another mistake, because you can give it to see this example, x, h star x, which is consistent, and the prediction that you are making is wrong. So you made the algorithm makes two mistakes. So that means that if you make one mistake, you basically identified the correct hypothesis. So if every time you make one mistake you identify, you need to output the same output. Now let's extend this idea to Littlestone dimension 2.
Well, you can ask a question from the chat. Someone asks, I think it relates to a couple of slides back. Are there versions in which the learner has some control over the order of the examples?
In online learning? So no, in online learning, you want him to get the examples sequentially. So it would be hard to let him control the order, because he doesn't know what he's going to see in the future. So I don't know of such a model where there is some leniency in this sense.
Thank you.
Okay, so if the Littlestone dimension is 2, then again we have two cases where it is unlikely that the algorithm makes mistakes, or it is likely that the algorithm makes two mistakes, and these two cases are completely the same as before. Either the original hypothesis is okay, or we basically identified the right hypothesis. The only problem with Littlestone dimension 2 is what happens if the algorithm makes a single mistake, and then the idea is basically to make the algorithm makes more mistakes. And how we do that? So again, we have two cases. First, what if the algorithm is already by chance globally stable? Then in this case, we don't have a problem. And if the algorithm is not globally stable and makes only one mistake on a typical sample, then let's consider the output over two samples. Then we get two hypotheses that are different because the algorithm is not globally stable. And then we're going to find some x that they disagree on, and we're just going to guess the label. Now with probability half, we're going to guess it correctly. And let's assume for simplicity that H1 is wrong. So we're going to run the algorithm on this sample, S1, and add this point that we guessed its label. And the algorithm is going to make two mistakes. So we basically generated more mistakes. So to summarize, what we did is we constructed a sampler that generates a sample that is going to make two mistakes, and you're going to get with some positive probability a new sample that is consistent. Okay? And you can imagine how this procedure continues. You have Littlestone dimension 3, so you until you stabilize the algorithm, you just keep on guessing the new points and so on until the algorithm either stabilizes or makes the maximum number of mistakes possible. Okay. So now I want to go over the second part. So the third part, about private uniform convergence. So like I said, what is a private uniform convergence? It's a private version of uniform convergence, where what we want to do is we want to have, given a sample, then we want to output a new probability so that for every age, we can estimate the prediction of age over this empirical sample, and it will be close to the real one. So it's not just learning. We want that it will work for all hypotheses. And now we also require privacy. Okay, so if this is uniform convergence, now we also require privacy. So we need to output this sample this probability in a private manner. Now, this is completely equivalent, and perhaps it's much easier to think about another notion called private synthetic data. So what is the private synthetic data? You have an algorithm that receives the data set, and you want to output a new distribution that is differentially privately fooling, which means that the expectation of every hypothesis in your class, or every, you would call it discriminator in this setting, behaves roughly like over the real distribution. So this synthetic distribution looks exactly like the real distribution if the tests that we're making come from this class, and the synthetic distribution needs to be private. So given the data, you output the synthetic distribution privately. Now, actually, when we started working on this, we were not necessarily interested about the private uniform convergence. What we were interested in is synthetic data in general. So synthetic data not private is actually a problem that is taken a lot of focus lately in learning. So this is an example of synthetic faces that were generated by a learning machine that saw faces, and then the machine basically generated all of them. You can go to this website called This Person Does Not Exist, and it will generate more of these faces, which completely look like realistic. It's not a problem in privacy. It's just a problem in learning where you have data and you want to generate data that looks similar to it. And you're probably familiar with the generative adversarial networks, which is, you can think of it as a framework to generate these types of synthetic data, where you have a sequential game between what is called a generator and a discriminator. The generator proposes some synthetic distribution. The discriminator tries to distinguish between real and fake. If it cannot, then the generator succeeds. And if it can, it outputs some feedback to the generator that keeps on improving the synthetic data until the two become indistinguishable. Now, and this is a very interesting model, and as you can see, it leads to some remarkable results. But from a theoretical point of view, it really is a challenge to try and study these algorithms, and even to theoretically model them is kind of a problem. Because one thing you might want to think is that you can model these algorithms, basically they receive data set, and then what they do is they basically learn distribution that fools the discriminator, in the sense that for every test that the discriminator can make, the real distribution and synthetic distribution look similar. But the problem is that there is a very simple solution to this problem. You can basically take the empirical distribution and it will satisfy this. And this is what the fundamental theorem said. It said that an empirical distribution over enough data looks like the real distribution in this sense. So to model or to understand synthetic data generators is a challenge, because even to say what is the objective, it really is a problem, because if we just define it as a fooling task, we want to make the discriminator be fooled, then basically memorizing your data is enough. So it's like saying, I want to generate a machine that listens to pop music, and then it generates new pop music. And then what the machine does, it basically just outputs the pop music that you taught it. And you call this generating new music. Obviously, this is not what you want. So you need some other definition if you want to actually understand what these algorithms are doing. And in this sense, privacy turns out to be relevant, even if you don't care about privacy, because you can think of basically private sequential generators like this, in the sense that let's assume that the discriminator at every round avoids leaking information about the data set, and the generator needs to be trained on this feedback, which doesn't disclose information about the faces. Then in this case, what you would get is you would get the generator from one perspective needs to output something that looks like the real images because it needs to fool the discriminator. On the other hand, you can inhibit it from actually copying the data set. Because by making sure that the discriminator is private, the generator basically never got to really observe the real data. So it cannot just memorize or do something that you don't want it to do. So you can even think of private synthetic data as some definition of what it means to generate data synthetic and still not copying the data. And what we showed is that private learning implies private synthetic data. In other words, whenever you can privately learn, if you have a discriminator that can see synthetic data and learn to distinguish it, but give some private output, then you can make sure that this sequential game is going to lead to sequential data in the following. So I'll spend in a minute. So, but the way we showed it is basically once we have a private learner, then by the result we talked about before, we know that the Littlestone dimension is finite. And then in this third result, what we showed is finite Littlestone dimension implies that you can make sure, or you can construct a generator that, given this feedback from the discriminator, after a finite sequence, after a finite number of rounds, he will basically generate data that fools the discriminator. And it's kind of analog to this mistake-bound model, where every time it outputs data that doesn't resemble real data, then it basically makes a mistake, and the discriminator can output some function that says that he made a mistake, and you get sort of like a mistake bound. You get that the number of mistakes he can do will be bounded. Eventually, the data will resemble the real data. Okay, so I think I will end here. I will not go into the proof of this result. And if you have questions, then you can ask questions.
First of all, thank you, Roi. Let's unmute and thank you.
Thank you.
Thank you very much.
Thanks.
Thank you very much.
Okay.
So we have one question at the chat. Someone asked, what exactly avoids the adversarial to learn the true distribution? I think you mean prevents the adversarial to learn the true distribution.
Again?
What exactly prevents the adversarial from learning the true distributions?
So which, in this setting of the generator or so the question is, why would the generator not learn the true distribution?
As far as I understand it, maybe the person who asked the question wants to jump in, or otherwise I think that's what they meant.
So there is one question. Okay, maybe I should have talked. So there is another. You could. There are many results that are trying to model GANs as saying basically that what the generator is trying to do is to learn the true, what is known as the true distribution. There is some real distribution, and then the generator is trying to learn it, and it actually outputs the real distribution. Now, such result, in order to prove them, you need to make some assumptions on the true distribution. For example, you could assume that the data is Gaussian, and then the generator, by learning the mean and the total variance, the variance, would actually identify the true Gaussian. So you do have such flavor results in this line of words. There are two caveats with it. First, when it comes to real data, what are the assumptions that we can make on the real data, on its structure that we can make, and then we can assume that the generator has learned it? It's really hard to think of such assumptions. And then also it's really hard to even verify them, because we actually don't know the real distribution, we only have data. And everything we do is in terms of the finite information we have. So at best we can hope is that the generator would be able to generate a distribution that is close to the real, in the sense that we cannot find statistical tests that distinguish. But to actually assume that it actually learns a true distribution, for example, of faces, that is quite unrealistic. And also unnecessary, because what we actually want is we want data that looks as real as far as we can see. But definitely there are results that assume that you could learn the distribution, but you would need assumptions.
Thank you. There was another question, I think, from the same person. The privacy models seems to consider small perturbations in the data set, i.e. changing one example. In the GAN setting, you can produce many examples that might have a significant change. Or,
yeah, so what the privacy assumption, what the privacy constraint would say is that basically, if this is your data set, changing your real data set, changing one of them, changing one face will not necessarily cause a big difference in the output that you see. Which is in some sense, if it does happen, think what happens if privacy is breached. Basically, it means that there is some face in your data set that the output that we see is very much dependent on it. So in some sense, but what you did is you basically memorize it, or you outputted you relied very strongly on the information in that face. So for example, if you would memorize it, if you would just output the faces that you saw, that is exactly what's going to happen. And that is exactly what you want to avoid. You want to avoid that for any of the pictures, you did not copy it or just generated some altered version of it.
So in some sense, it's sounds similar to avoiding overfitting by other means.
Yeah, you could say so. It is a question of what it means to overfit, because in supervised learning, it's very clear what it means to overfit. But in these kinds of problem, generative learning and unsupervised, what does it mean to overfit? That's elusive, and you need to model it and you need to define it. So you could say that what we suggest here is privacy could be a definition for overfitting.
Okay, I think we're almost out of time. If anybody has one last question. Otherwise, we can just thank the speaker again. So thank you, Roi, for a very interesting talk.
Okay. Thank you, Roi.
Thank you.
Bye.
Very much.
Bye.
Thank you.